Thursday, we talked about torque and computing torque. On yesterday, we talked about computing moments of inertia. And now today, we put it all together with Newton's second law for rotating objects. Along the way, I'm going to address what we did not finish yesterday, and that is moments of inertia for extended or continuous objects. Okay?
Are we going to do homework?
Maybe. We'll see what we can get done here. So I want you to imagine that we have an object of mass m, and that object is free to rotate about a point O here. Now I have this object on a string, and what the string does for us is it keeps the distance constant, right? And so we're going to apply a force to our object, and that force is going to be exerted on the object continuously as it rotates. And the distance that the object is from the point of rotation is r. So, let's consider now the motion of the object from the perspective of Newton's second law, F equals ma. Force equals mass times acceleration. Pretty simple. And because the force is tangential, then what we get is a tangential acceleration as this object moves in circle of radius r. There's our circle. Okay? So the motion of the object is force equals mass times acceleration. But now if I want to consider this from the point of view of torque, I would compute the amount of torque that is exerted by this force. And that torque is force times distance times the sine of the angle between, and because the force is tangential, it is always perpendicular to the radius of the circle, and the sine at 90 degrees is 1. Yeah. And so we have force times radius times the sine of 90 degrees equals mass times acceleration. This quantity here is simply the torque about point O. And this quantity here can be written in terms of the angular acceleration. Wait, I failed to multiply both sides by r, didn't I? There we go. That's much better. So we have force times r equals mass times acceleration times r. And because this acceleration is a tangential acceleration, I can represent it as r times alpha. Thanks, Jonathan. So that the torque exerted around O is equal to this quantity mr squared times alpha. And as we saw yesterday, mr squared is simply another name for the moment of inertia of the object. So that what we end up with is torque equals moment times angular acceleration. This is Newton's second law in a rotational sense. And it is an exact analogy for F equals ma. Torque equals I alpha. Yeah.
Yesterday we were going to go into extended objects.
Yeah, we'll do that. Yep. Saw another question over somewhere.
Why is the radius on the right hand? 5.
So, to get from here to here, I multiplied both sides by r.
Okay.
Yeah. Except that I forgot to. I was first going through it and then come back and fix it. What if I have a system of objects? Well, the same kind of thing is going to apply. If I have a system of objects, then the total torque is now going to be distributed over all of those objects, and we simply get the sum of the mr squared times alpha which gives us, once again, the moment of inertia times alpha. So this is newtons second in its rotational form. Hand. I saw a hand. Heidi, I think it was your hand earlier.
Oh, no, never mind. I figured out what my question was.
Cool. Okay, great. Now, what I'd like to do is to see how this works out. And at this point, I want to talk about extended objects. So I want to imagine that I have a solid bar. Maybe my solid bar is 0.48 meters long. And maybe it has a mass of, oh, I don't know, let's call it 200 grams. Like this, which is 0.2 kilograms. And I'm going to pin this at one end so that it's free to rotate. And what I'd like to know now is, if I simply hold it out there and let it go, then what kind of angular acceleration will it experience right when it is horizontal? And so we're going to begin where we always begin, three-body diagrams. We're going to put forces on this thing right here. There's going to be a force of gravity, and the force of gravity is going to pull straight down through the center of mass of the object. And there's also going to be some force at the pin, at the pivot point. It will be a normal force that will keep that pivot point from being dragged down together with the object. So we can say that the sum of the net torque on the object, sum of torques, about our pivot point O, is equal to, and here is our second law, I times alpha. And so we walk down and we add them up. The torque exerted by the normal force here is going to be force times distance, and the distance from the normal force to the pivot point is 0. So we see what we saw again yesterday, that a force directed through a pivot point exerts no torque. Meanwhile, the mg is pointing down at a distance of, what will that distance be? 0.24 meters, that's right. Times the sine of the angle between, which is invisible. And is this a clockwise or counterclockwise torque? Clockwise. We picture it acting, and we see that we're going from 3 o'clock down to 6 o'clock here. So we're going to take that as a negative value. Put in the m and the g, and this gives us negative 2 newtons times 0.24 meters, or negative 0.48 newton meters worth of torque, equals. So now over here, I times alpha. Now, what about the I? And here's where we talk about extended objects. The bar is not one point mass. Unlike the other objects that we have worked with before, instead, the bar is made up of atoms, and each atom is going to have a mass of like 10 to the minus 25th grams or so. There are bazillions of atoms in this thing, around 10 to the 24th, yeah, 10 to the 24th or so atoms in this bar. And if I were to try to do mr squared for all of the atoms, that computation would take so long that no computer would ever finish, right? So I can't possibly do that. So what I'm going to do instead is to appeal to a calculus idea. First, I'm going to give you the concept, and then we're going to see the results, which are printed in our book. The concept is that using some calc foo, we're going to take the bar and we're going to divide it up into lots of little tiny segments. And we're going to add up mr squared for each segment. And the r is different for each segment. And so you can imagine that we end up having to do some kind of fancy version of addition. It's called integration. And when we do, then we get an interesting result, and that is that the moment of inertia of this entire bar about the end here is 1/3 of its mass times the square of its length. Poof. This result shows up sort of from nowhere via calculus. Now, if you do AP Physics, then we actually go through the calculations and they're not hard, but because we don't know how to do integration, I'm not going to bother. That makes sense? But what that means is that when we encounter certain types of objects, we have to look up their moments of inertia in a table somewhere. And fortunately, your book has such a table. So everybody turn your books to page 208. And on page 208, the book gives us a table of moments of inertia for common objects about their centers, usually, or sometimes about their ends. So notice we've got two things going on here. We've got the object, and we've also got its point of rotation. And here we're talking about the long thin rod, the long uniform rod, it's called, of length L, about the end, which is the second from the bottom. Everybody see that there? And so we can use the formula that's given there to compute the moment of inertia for this rod, which is going to be 0.2 kilograms. Times the length, which is 0.48 meters squared, just like that. Yes, sir?
Can you explain again, like, the whole concept of using, like, the, like, how you get this moment of inertia?
I can explain the concept, but I'm not going to be able to show you the computations until you take calculus. But the concept is that because we have an extended continuous object here, I'm going to visualize splitting it up into lots of little tiny pieces, and each piece is going to have a little mass, we'll call it dm, and each piece has its own radius, right? So the radii are all different.
Yes.
And so now using super duper calc foo, we add up r squared dm over the entire object. And when we do, out comes this.
So the L, what does the L stand?
The L is the length of the rod.
So why can't we just use, like, the center of mass for that? That'd be easier.
Hey, that's a great question. It turns out that if we just use the center of mass, does everybody see that? That would be a reasonable approximation. But if I use the center of mass, then I would have a distance of L over 2.
Right.
And what I would get is m times L over 2 squared, which is ml squared over 4. And you can see that that actually underestimates the moment of inertia by a little bit, by 1/12. And the reason it underestimates is that the mass that's out here, the half of the mass that's further out, counts more than the mass that's closer in.
And why is that?
Well, because it's further out. It has a farther distance.
Oh, yeah.
It's at a farther distance. And so I end up underestimating because I'm pretending that all of the mass is concentrated at L over 2, and it's not.
Makes sense.
Yeah. That's a really good question. If I were stuck in the wild and I didn't have values like this, I would do that kind of estimation that you're talking about, but I would know in my mind that it's going to be a little bit too small. Okay? What does this value turn out to be when you actually compute it? Oh, you people got caught staring again. Don't stare, compute.
Minus 0.1536.
Which turns out to be not that much, right? So that now when I do the division, what do I get for my alpha? And that's going to be in radians per second squared. Why such a large alpha? Because I had a small torque, but I had an even smaller alpha. And so when I divided small by smaller, I got a large value. Question, Blake?
When did we find the torques?
We found the torque from the free body diagram right here. And we walked through and did force times distance times sine of angle between.
Where's the answer?
Here, here, here.
Oh.
See it? Better? So there's two things about today's lesson. One is that we're using the general idea of torque equals I alpha. And then the second is that we understand that extended objects are going to have special formulas for their moments of inertia, and we can find them in a table somewhere. And the table in your book is pretty good for all the things we have. Curious about something. I never asked this specific question. You know the Harlem Globetrotters? Yes. And they do the whole spin the basketball in the end, right? So I wonder how much torque is needed to get the basketball spinning. How would you go about figuring that out? Now, this is a very ambiguous question. We need to nail it down here. What do I need to figure out in order to make this work? No, we need the mass of the basketball. Yeah, anybody know that?
Look it up.
You can look it up. Look it up.
The radius or the diameter of basketball.
No, mass.
Yeah, we
We
also
need
use
both,
it.
yeah.
kilograms.
0.62. Okay. And the radius?
Uh, 1.5 inches. Which is like what size do you use?
29.5, I think,
Well,
Well, I don't know if it's the diameter.
Well, 29.5 centimeters is almost a foot.
That's probably diameter.
It's definitely
about 11.75, 11.8.
Well, it should be 29.5 divided by 2.
2.2?
Hey, 29 divided by 0.4. No, I'm on about inches. I'm on about inches.
We don't want inches.
And 14.75 centimeters would be how many meters? 0.1475 meters. Okay, good. Very good. All right, what can I find with this information here?
Inertia?
I can find the, not the inertia, but the moment of inertia, right. Inertia is just another word for mass. Right. So the inertia is 0.62 kilograms, but the moment of inertia, and the moment of inertia about what point? About the center, that's right. So we look in our book for handy dandy formula, and what do we find?
2 divided mr squared.
Yep. And that gives us the moment of inertia of the ball. You're staring at me again. You should be computing. Got it, James?
Yeah.
Two, four. Yeah. Yep. Okay. So we've got the moment of inertia of the ball. All right. Good. Coming back to our question, how much torque is needed to get the ball spinning? Yeah.
One question. For page 208, we can memorize all these.
No. I'm glad you asked that.
Oh, no, but
Yeah, you do not need to memorize all those. The idea behind a table like that is that you can look them up as needed.
Okay.
So, generally the way it'll work is on a quiz question, I would give you I for a particular object
Okay.
that you're looking at. Okay, so how much torque is needed to get the ball spinning? And so we have now the moment of inertia of the ball, and what's needed now is our equation, and that is Newton's second law here, torque equals I times alpha. We're looking for torque, we have I, therefore we need alpha, okay? Let's see here. Alpha refers to the angular acceleration that the ball experiences. What do you think about that?
Slowing down. One. You're not touching it, slowing down.
They're not touching it slowing down, but I'm asking you about getting it to go to begin with. What's that? It's speeding up, that's exactly right. Can we get any numbers on that? What kinds of numbers would we want to have? We'd need velocities, wouldn't we? Because the alpha is the rate of change of the omega. Do we have any angular speeds, really, for this situation? Start with the ball. I'm doing this. We probably are going to have to estimate some revolutions per minute or something like that. So, when the ball is going as fast as it possibly can, how fast is it going? Somebody do it with your fingers. How fast is it going? So how fast is that? The revolutions? 7 revolutions per second?
Some of the, like,
It seems a little fast.
some people do it really fast.
Yeah, it does get going pretty fast. So like this, how many revolutions per second is this?
Okay, they're not.
Wait.
They're
I have an idea.
5? Not 1 second.
I have an idea.
Yeah.
What if you got a basketball, put a mark on it?
Yeah, I think like
Took a slow-mo camera.
Totally.
See how it actually goes.
I'm actually good at basketball.
This speed, that's not.
I can actually do it.
Earl can do it.
Yeah.
Just, why don't we have Earl test it? It doesn't matter, we only need it for like 3 seconds.
Yeah, you don't do it for very long.
We even have time though.
Yeah. Oh, do we have time? Yeah, we'll have to get that from our video also, won't we?
We'll need this for tea.
So notice that a lot of, let's call it home physics you do at home, is just a matter of paying attention and asking, I wonder how much? It's a matter of measuring. While we're doing this, does anybody want to take bets on how much of an alpha we're going to get?
Half, or, yeah, 1/2 reading.
A half reading per second squared? Okay. So we've got Blake is
Wait, can we put something on this bet? Like 50 cents bet in there and winner takes all?
I'm good. I'll take brownie points. I'll take brownie points. We'll bet brownie points, all right.
Wait, so we
Wait,
lose all the
who-
brownie
who
points?
has brownie points? No, it's strictly bonus. Winner gets brownie points. What you got for your number? Okay, think for a second. Estimate number of revolutions per
Oh,
second.
wait, I take that back. You're taking it back?
Sure.
Okay, 2.
2.
Starting from rest.
Right. And is it 2 radians or 2 revolutions per second squared you're talking about?
Gradient.
Radians. All right. Fair enough. All right. Everybody's got to place a bet here. 4.
Wait, are we allowed to, mark this?
Lydia?
Wait, is this alpha or is this speed?
Alpha, the acceleration. Yeah.
Oh.
Wait.
3. All right.
On the air.
What you got?
I'm still thinking.
Still thinking. Yeah.
I was gonna say 2, but it's good.
That's fine. You can take away. Yeah. Heidi, what you got?
10.
10. Samantha. 5. Catherine. 2.5. All right. James. 3.5.
It's gonna be like 10,000.
What you got?
Well, considering all the ones I wanted to make, I'm going to go 3.25.
3.25. Jonathan.
Let's go point back.
0.5. Peter.
6.
6. MS. 7. Earl.
Let's go like, yeah, 300.
300.
It's gonna be like 3,000.
What you got?
It's gonna be like
2.75.
This is.
What you got?
3.15.
3.15. Okay.
Change my answer.
Oh, shoot. 96.
I want to change my
Can we
answer.
microphone and resolution?
You can.
The same number.
You could do yours in revolutions per second squared, yeah?
I want to change mine
To what?
I want to change mine to 102.
102. Wow, you guys are getting awfully specific. Excellent. Okay, so we have a bunch of predictions here. And now we're ready to actually test this. And we're going to need video. Where'd Blake go?
I need tape to it, Dave.
Excellent. And we're going to need somebody to video this. And what we're going to do is to count.
Wait, how big is that?
Jordan never gave me.
It was probably guys.
It's only 5 though, so we own 5 back.
Fantastic.
Long.
All right. So let's be clear about what we're doing here. What we're going to do here is to assume that we're starting from rest, right? And therefore, the delta theta through which this turns should be 1/2 alpha t squared, because omega 0 is 0. Omega 0 t equals 1/2 alpha t squared. And so we should be able to, just knowing the time and counting the number of revolutions, be able to estimate the average alpha from that. Does that make sense? All right? So, Earl, who's videoing? You got slow-mo on yours? Excellent. No, we're not. No, it's you. And make sure that the video captures from rest, right? Because our section is starting from rest. Okay? Let me know when you're ready to go. Can you see the blue thing?
You can do it.
Come on.
Yeah, you just have some watermark that you put.
Yeah.
He's not happy.
I told you I can't do it that long. I can do like.
Okay. That's. Do we agree that those are pretty uniform? That all three of those were pretty much the same rate?
Yeah.
Well, let's check.
Hold on.
Oh.
He made
I'm more of
can't
a
shoot.
I'm more of a shoot.
Tommy's more confident. He told me he can't shoot.
Then, well, which way do I want? Do I want this way or
You
this
just
way?
press the blue shirt.
Yeah, we want the blue to be in the center. So like,
Is that better?
Okay.
And then rotate from the
All right, slow-mo it for us and tell us how long it takes to go a certain number of rotations. Yep. It gives you times on there, right?
Don't throw it off.
Yeah, shoot.
You don't do that. You press up on
You look pretty funny in slow motion.
I look pretty funny right now.
Well, shoot. That's the.
Isn't that weird? I mean,
Oh, what are we gonna do? It doesn't give us a time marker. Count.
why would it not have power? It's like 0.25.
That works. That was 5 rotations. But how long did it take?
It doesn't, really didn't have a thing on top.
It has a thing on top, and what is it?
Apple's really,
What's the speed of a slow-mo? Because if it's 0.2 seconds.
What? What? What are you talking about? Do we know at what rate it slows down the time?
And it tells you how many frames per second.
You can probably Google that.
Are you
we're talking
talking
about
You
Oh,
video
yes.
it, you can take down how many frames per second.
how many frames per second?
It's probably, it's probably 240, but you can go between 120 and 240.
And 60 normal?
Probably.
So it's a 4-to-1 slowdown.
Okay.
The amount of time it takes is 4 times as long as
You're on 120, so it's half.
So it's half. That makes sense. All right. So somebody get their stopwatch ready. We're actually going to count.
I don't have the right. So I don't know.
I'm going to tell you when to start with your stopwatch.
He doesn't know. He doesn't know.
Yeah,
Okay? I'll tell you when to start, when to stop. And go. 2. Stop. 3.66, and we multiply that by 2. Excellent. Divided by 2.
Oh, no, it's like 1.8.
They don't.
Now, all of our answers over here were in radians per second squared, so we need to do a little converting. That's 2 pi radians per every revolution. So that's going to give us
31.4 radians.
31.4 radians. Equals 1/2 alpha times 1.88 squared. Sorry, 1.38 squared. That's terrible. 1.84, 1.83 squared. My arithmetic circuit's fried.
18.
So we have 31.4 times 2 divided by 1.83 squared. Gives us an alpha of 18.75.
Is anyone close? Be honest.
Radians per second squared. We compare that here. We had a whole bunch that were under 10, and we had a 96, a 102, and a 300.
Wait, what was it, 5 revolutions?
It was 5 revolutions total. That
I said mine was 3.15 revolutions, not radians.
3.15 revolutions. Okay, so we would divide this by 6.
Did I really?
Yes.
Yeah, how about that?
No way.
So
Everyone doubted me, except me. No,
5,
stop. Hey.
and we get 0.8.
Oh.
That doesn't seem right. That should be, hang on a second. One more time. 18.75 divided by 2 divided by 3.1. Yeah, it's 2.98.
So I got
radians per second squared. Yeah, I think you win the brownie points here.
Yay.
Yeah. 10 brownie points for you.
Okay.
Okay.
Good job, Evan.
What did we learn from this? Well, there was some trial and error that went on, right? We had to figure out how to do some stuff that we didn't know how to do. For example, we had to figure out how to measure the amount of time that it took to spin. We had to figure out how to measure the alpha. Once we had that, though, the computation of torque was actually fairly straightforward. Well, we haven't finished it quite yet. We need to actually plug in. We have an I of 0.0054 kilogram meters squared. And we have a torque of 18.75 radians per second squared. Which gives us 0.1 Newton, well, let's see, it's kilogram meters squared per second squared. And watch this closely, as Newton is a kilogram meter per second squared, so these units are in Newton meters. 0.10 Newton meters worth of torque. In other words, there is not a lot of torque required in order to make all that happen. And that makes sense, because if you had to use a large force, you'd end up just knocking it off your finger, right?
So who wins the brownie?
Evan does, yeah. Evan. What's that?
Do I get brownie points for spinning it?
No.
Do I get brownie points for almost getting right?
You're pretty far off, actually.
Well, Evan was closer than you, as it turned out.
Because I said mine was in revolutions, not radians.
Yeah, everybody else had radians per second squared. And the answer there was 18.75. Evan was about 3 revolutions per second squared, yeah. Okay, at this time we have a little bit of time for homework questions if you have them.
I don't want to ask it.
I have one.
Go.
Can I go get my book?
Number 31.
Yes.
31.
I
And I think Blake gets to do this.
No! Now I want to.
Little M and big M. Big M and little M. Alright, so we have these objects here. I guess it's actually done rigidly, so we'll go ahead and complete the lines. And what they're asking for is the moment of inertia about a couple of different axes. They also ask, part C, about which axis would it be harder to accelerate this array? We can actually do that one intuitively. Taking a look at it, which axis has the masses further out?
Oh, that's my bad.
Definitely the vertical axis, right? The vertical axis puts the right side at a much further distance than the horizontal axis puts the masses there. So we can immediately see that the answer to C is the vertical axis would make it harder to realize without even doing any computations. Now let's actually do the computations for the vertical axis. And they give us a distance, 0.50, and what is this distance right here?
4.5.
1.5?
One. Oh, gosh, no, only one.
Okay, great. And what are the values of little m and big M?
Little 1.8 is 3.1.
1.8, 3.1. What is this thing, by the way? Do they tell us?
No idea.
It's just some random abstract object. Okay.
Wait, is this supposed to spin?
Yes.
That's the question.
Yeah. Okay. And so now, we're simply going to go through and add up mass times the square of the radius. For A. But also for B, it's just that in B, we have a different radius. The only thing that changes between A and B is that the radii are different. All right, well, start. How many masses do I have?
4.
4. So I'm going to have 4 different terms. Yeah, go.
You have 1.8 or 1.8 times 0.5
Squared.
squared
Yep.
plus 1.8
Uh-huh.
times 1 squared
Yep.
plus 3.1 times 0.5 squared
Yeah.
plus 3.1 times 1 squared.
That's it. No sweat.
Where's
Yeah.
the origin at that we're like looking at?
We're talking about the vertical axis, and therefore you're going to use this as the basis for your radius. So notice that the radius for this guy will be measured like so. The radius for this guy is going to be measured like so. Yeah, easy. Good job. We made it easy. 3.1 times 0.5 squared, don't know off the top of my head. This is 3.1, this is 1.8. That's going to be 0.45. Is that right? Excuse me. Excuse me. And this one would be, let's see here, that's close enough to 3.2, right? So 3.2 divided by 4 should be 0.8. Take it down by 0.25, so 0.775. That's what we get. Add them up to carrier 1, or carrier 1, and I believe we get 5.425 and 5.4 kilogram meters squared. Is that right? You got 6?
Supposed to be 6.1.
I probably did some arithmetic wrong somewhere. Where though?
The 31 times 0.5? Because the rest of it I know is
Yeah.
Yeah, it has to be the 3.1 times 0.5. Yeah.
No, I get that.
They're all right numbers, it's just that adding them.
Yeah, I get 6.1 when I do this, like so. I probably, what did I do here? Yep, 2, carry 1. I think I dropped my 7 here. So we get 6.1 kilogram meters squared. There. Good. So how do you, did that answer your question?
Yes.
Okay, and then part B is very similar.
My problem with this one is the first time I did it, I used a different equation. I used 1/3 squared.
Ah.
I thought they were.
Okay, good. Yes, so let's see why that equation doesn't work and this does. The table that you have here is for objects that are extended throughout space. In other words, the 1/3 ml squared is for a bar that has mass all along its length. We don't have that here. We have mass here and mass here. Those are point masses. So we're going to use the ml squared.
I figured that out afterwards when I went back. So the reason why we haven't been doing like this type and instead we've just been doing MA is because it's just been point and not actually like amount of space.
Yes, that's right. We had not done extended objects until
So that's why now we're doing the immersion stuff.
the concept, torque equals I alpha, is the same throughout. It's just the computation of I is different. If your object is a solid object with mass distributed throughout, then you've got to do some kind of calculus. If your object just consists of single points that that mass student, then you can do more school. Good. All right, let me call this.